So we've got the last kind of short topic of today, which is kind of going through what we have seen of different kinds of models so far, right? And this is about what you see in GAMS. So this is specifically dealing with what are the solvers that you have to be using for specific problems in when you're solving problems in GAMS. So in GAMS, you've noticed that there is one sentence after your model description, all the equations and the model statement. There is one sentence which is something which goes something to the effect of, if I can maybe write it here. So it says something like solve, and then some model name, the Markovich model, solve this, and then it says something like maximizing some objective, and then using, and then something with normally three letters or maybe 5 letters. So it could be something like using LP, right? So this could be a solver statement in GAMS. You have so solve is a keyword, maximizing is a keyword, using is a keyword, and LP is a keyword. Your model name is the name of whatever name you have given to your model, and up here would be the variable. It has to be a free variable, by the way. It's the free variable that you're optimizing in your model, either maximizing or minimizing, right? So this is your model name, and this is a free variable, which is your free variable representing your objective function. Representing the objective function. So in the Markovich model, the objective function is simply the whole term, the 2 terms, right? You say you have to set your opt equal, return minus risk, right? Right. But the purpose of this slide is to look into this last term here, using something. So can somebody tell me what LP stands for? Linear programming, right? So what is a linear program? Right? So that's not the case in the case of Markovich, for example, right? But yeah, so LP would be the case where you have a linear model, means that in a linear model, for example, you're not allowed to multiply variables with each other, right? Because then makes your model nonlinear. You're not allowed to take the logarithm of a decision variable, or you're not allowed to have the power function or an exponential function or things like that, right? So anything which makes your variables nonlinear, either in the constraints or in the objective function, is not allowed in a linear model. So when all the terms are linear, then you can use linear programming. And the LP solver, there are some different LP solvers. Most of them are quite efficient today. So solving a linear program where all the terms are linear actually is quite effective. We have very good algorithms for solving those. Anybody can mention maybe what is the names of one algorithm for solving a linear program? The simplex algorithm. Yeah, there's another one also. If maybe. Yes, simplex is actually an algorithm, right? But there is also another one, another method. So there's a solver called Cplex, but then the algorithm for solving LPs is called Simplex. I think probably Cplex was kind of inspired from the simplex method because that came first, and then the Cplex solver came somewhere in, I think, in the 80s. And the simplex method have been around since 1940s, more or less. It was used during the Second World War, actually. For logistic optimization problems. So people were doing it by simplex tableaus in hand, and then later it became into software, right? But then there's another more efficient method for solving LPs. Have you heard of interior point methods? right? So you know that the simplex method goes from the boundaries. You have you have your feasible region, and the simplex tableaus, they move from the boundaries of your region. And if you have like a feasible region with hundreds of thousands of dimensions, right? Then moving along the boundaries to get to the top or to get to the bottom, depending on if you're maximizing or minimizing, could take quite a long time. So the interior point method is something which goes from within, at its sense, kind of a trajectory towards inside the region, and then it finds out, okay, now I'm getting out of the region, it goes back to the region. So it kind of shortcuts in the feasible. That's a more efficient way of searching towards, you know, ascending or descending in the feasible region. So these are two methods. But in both cases, also, I mean, there are the simplex. There are many enhancements on the simplex method, which makes it quite efficient as well. So as far as this course is concerned, you just have to know that whenever a problem is a linear program, then they are easy to solve, no problem. You can just write, you know, using LP. And as far as the model is LP, then you're home safe. So if you can keep your models into linear program, then always is a good idea, right? They're easy to solve. There are both free solvers, open source solvers, and also good commercial solvers which solve those problems, no problem at all. Well, that was for the LP. But then comes the next one, where we introduce this 0, 1 variables, like the one I just did here for counting, right? So this one for counting how many assets I had in the model. And if I did that, then I can't use the LP, then I have to say using MIP. So MIP, that stands for mixed integer program. And a mixed integer program is mixed because you have both kind of, it's a linear program, and then you have the 0, 1, or it could be integer variables in the model. Then you have to use the MIP solver. So anybody has heard of a method, because you can't use simplex alone any longer for solving these models. What is kind of the paradigm of all the algorithms for solving mixed integer? There's a course here called mixed integer programming, or integer programming, I think it's just called. What is, anybody has had that course already? You're taking it? You haven't got that far yet? A long time ago? There's something with branch and bound, right? So essentially branch and bound, or if you go all the way, then it's branch and bound and cut. So essentially then if you want to solve mixed integer problems where you have the 0, 1 variables, essentially branch and bound and cut is sophisticated brute force, right? So because then you have to look into all the choices. If I put 0 here and 1 there, what happens? And then I shift it back and put 1 here and 0 there, what happens? What happens, you know, and then goes on with all the variables, all the combinations of zeros and ones. That would be brute force. It will go forever. It will be a never-ending story. So obviously, a course like integer programming is about how you do that in a much more sophisticated way, so you don't do all the combinations. If you want to do all the combinations, forget about it. You can't really solve those problems in any way efficiently, as far as they have larger a certain number. But there are ways, especially when you're talking about bounding and about cutting. So you essentially, you know, you are bounding the problem, and then you're cutting it, making it smaller, your feasible region all the time. Or you're making sure that the optimal region is confined within an area where you cut. So there is a lot of theory on that. Again, we're not going to go through any of that, but the important point in this class is that you have to know when you have to use LP, when you have to use MIP, right? So here we'll be kind of using those methods, and we have the Cplex solver. And Cplex solver can be used both for LP problems and also for MIP problems. I'll get back to it. It's also for a third group of problems called QCP and MIQCP problems, which is relevant for this course in particular. So Cplex is essentially Cplex and Guruby. We don't have Guruby in this course. We don't have license for it. But those two solvers are kind of our solvers of choice for solving the majority of the problems we have in this course. Those ones, and then the NLP. Is the question?
Do we have to download Cplex separately?
No. Well, the good thing about GAMS is that then when you get GAMS, then all these solvers come combined in GAMS. So GAMS calls that solver for you. It's already in the package. The only thing is that the only thing actually you do is that you're changing this one little keyword. Going from using LP to MIP, then GAMS finds the default solver for that. And then you can explicitly also tell GAMS, use this MIP solver rather than that one. You can also do that. Right? Otherwise, it would pick the default for you. Right, so that was LP and MIP for linear programming and mixed integer. The third one is the one that we used last week. It's NLP. Stands for nonlinear programming. And why is it? Now maybe it's just a question to you. Why is it that the problem we solved last week, the Markovich mean variance model, why is it nonlinear? What is it that makes that problem nonlinear? If you look into the formulation. Yes, there's the risk term, and can we be more specific?
Yeah, it's multiplying xz from both sides.
Right, so you have xi times qij multiplied by xj. So you're multiplying two variables, right? X times y, or in term xi times xj. That makes your model already nonlinear, right? So once you have nonlinearity in the model in whatever shape or form, then you can't use LP or MIP. Then you can use NLP. Now, the solver that we are using as default for NLP problems is called Conopt. It's actually a Danish company which stands behind that. It's a small Danish company which is only focusing on solving nonlinear programming problems quite efficiently. Then we have this special case where we get into very tough problems, like you have nonlinearity mixed with integer variables. So you have a min LP. Min LP stands for mixed integer nonlinear program. So whenever you start, whenever you start getting into min LP, just stop and think whether you really need the problem to be min LP or not, because the chances are that you can reformulate it into an MIP or MIQCP or even LP, right? So there are some kind of legitimate cases where you have no other choice but going along with min LP. But I would say then if you get there, then probably this has got nothing to do with this course. Then you have to find out how they can reformulate it so you can get back to the safer zone. Because when you get into the min LP realm, then it's deep water. The problems are getting too tough. There is no guaranteed optimality in any of the solvers we know. And remember, now we're talking about general nonlinear problems. So that means you have, in terms of nonlinearity, if you have this case, so this is a nonlinear kind of solution space landscape, right? And normally what the nonlinear algorithms can tell you, they can just find local optima, right? In general, there is no guarantee that they can find you the global optimum. But if the problem was of this shape, so this is what do we call this kind of nonlinearity? This one or this one, convex or concave, but normally we just call them convex. So convex optimization, so if you find the local minimum, you can also find the global, right? So that's why it makes the convex problems quite easy. So you need to differentiate a little bit within this course, especially because in a second we get into what kind of nonlinearity is in the Markovich model. Then you need to differentiate between this shape or this shape. This is kind of general nonlinear problems, and this is a convex nonlinear models, right? And if you are using the NLP can solve the general nonlinear problems. But then if you mix that with the 0-1 variables, where your solution space is kind of pointy, right? It's not continuous. So if you have a non-continuous solution space, at the same time you have a general nonlinear form, then the problems get extremely difficult to solve. And well, I mean, for one thing, we don't have good solvers. We don't have license for the best solvers which are out there for those types of problems. But even if we had, then they really don't go that far. They get better year after year, but there is really no guarantee for the quality. And if the problems get big enough, then you can't really use them effectively or have any guarantee in terms of the solution quality anyway. right? And we get into you have to use other methods. You have to then look into the problem itself, try to find out how can I come up with a specialized algorithm for this particular problem, use my knowledge of the problem to be sure whether the solution quality is good or not, right? But we are not going to go there. So my recommendation is to keep away from the min LP. So whenever you get in there, then let's have a discussion, see how we can avoid being in the min LP realm. Now, for today, though, we are playing a little bit with going from min LP to something which is called MIQCP. But before that, if the problem is convex, so if you have a quadratic problem, and quadratic problems are convex, then you shouldn't be using NLP, but you can be using QCP, which is more effective. So QCP stands for Quadratic Constraint Programming. And quadratic constraint programming is exactly the kind of problem that we have in Markovich. So that's the beauty of the Markovich, which is kind of one predominant model in optimization in finance. So the Markovich model is of this type. So the Markovich model is quadratic. So since the Markovich model is quadratic, you can use QCP. You don't actually need to use NLP, right? Anybody knows what is the definition of a quadratic problem? Or in terms of the Markovich model, let's say, what is it that makes it quadratic? So let's go to the plain vanilla version of the Markovich. So this is the one. You have the term here. That was the nonlinear term, right? xi times qij times xj. That's a quadratic term. That's nonlinear, but it's in particular that's a quadratic term. And there is some requirement for the matrix in between. The Q matrix has to be, which in this case is the covariance matrix. Sorry? Yeah. Yeah, this is something to that effect. Positive, semi-definite. Right. So probably that's something that you had in some algebra course some years back, happily forgotten. But actually, it's good not so much, that you need to, that you can go find out what is the definition of a positive semi-definite matrix. But essentially, a covariance matrix has to be positive semi-definite, right? So that means the Markovich model is quadratic. That means the covariance matrix is positive semi-definite. Now, if you don't want to go and check your covariance matrix for being positive semi-definite, because see, I can easily construct a covariance matrix, a fake covariance matrix, which is not positive semi-definite. And one way of you telling me that my covariance matrix is not valid is actually checking it and see if it's not positive semi-definite. Then you can say, well, it's not positive semi-definite, therefore it's not a valid covariance matrix to begin with, right? So just using the solver, the QCP solver, the QCP solver actually does that check for you. So you can test that. You can test that. You can just temper with your covariance matrix and then try to solve the problem using QCP. And at some point, it will tell you that the problem is not quadratic because your Q matrix is not positive semi-definite. So it will do the test for you before it starts using the underlying solver, because that means that the problem is of this shape. It's convex or concave, right? So that therefore QCP is specialized for solving problems of this type. Right? So that was the QCP. And here comes the interesting part. If the problem is quadratic, is nonlinear, but of a special kind of nonlinear, quadratic, then you can easily add also mixed integer constraints, like the ones with the size constraints that we had here, or the costs, the fixed costs that we are looking into next week. And then you can combine integer variables with quadratic constraint programming, and that's called MIQCP, which is the last one for today. MIQCP. So that's mixed integer quadratic constraint programming, and those are, we have CPLEX is actually an efficient solver for that, and there are other solvers which can quite efficiently solve those problems as well. So this is as much as we get into kind of the talk about algorithms, optimization algorithms in this course. It's important that you remember this slide, come back to it, and have an understanding of when to use which solver for which kind of problem. You have to have an understanding of whether the problem you're working with is linear, mixed integer, nonlinear, quadratic, or mixed integer, quadratic. Right? Any questions on the solver statements? Otherwise, we're done for the lectures today. So let's take a break until 2:45, and then we go on with the exercises.